In this video, we'll explore the steel beam command and how to place and configure beams in ideCAD Structural. You'll learn how to define beam properties, including section, material, elevation, and alignment options. We'll also show you how to create castellated beams and apply shear stud settings. You'll discover how to assign load parameters and use the divide command to split beams or adjust slopes. We'll cover how to work with inclined or horizontal working planes, model cantilever beams, and even define curved steel beams with custom geometry. Finally, you'll learn how to use the Select Similar command to quickly select and manage beams with shared properties. By the end of this video, you'll be ready to model complex steel beam systems with accuracy and speed in ideCAD. Next, we have the steel beam command. Just like with the steel column command, I'll first go over its properties, then move on to the details. First, I navigate to the steel beam command under the Steel tab. As you can see, the software highlights it in a different color when I hover over it. I click once, and the command opens. You'll see multiple options for modeling various types of steel beams. Just to the right, there's a drop-down menu where you can select the section type. As usual, I'll start with the settings icon on the far right. When I click on it, a new dialog appears. Just like with the steel column command, it starts with the steel beam name and continues with the material specification. When I click Load Section, the section library appears. As you know, the library includes the full ArcelorMittal section tables, both American and European profiles. You can either select a section from the list or type the name directly using your keyboard and press Enter. The material is currently set to S235, and if you want to assign a rotation, you can do so from the rotation field. The value entered under the Elevation tab defines the bottom elevation of the element relative to the story. By default, it is set to 0, which means the steel beam will be placed at the base level of the current story. There's also an orientation section, similar to that used for steel columns. You can set offsets in any direction as needed. It's currently set to top center, but you can activate user-defined, click once, and manually enter the required values. I'll keep it at top center for now. You'll notice that some of the fields are currently grayed out. I'll quickly show you how they become active. I go to the Section tab and select a castellated hexagonal profile. Let's say CHIP 360. A preview of the section appears in the small window. I click OK. Now you can see those previously inactive fields have become active. These fields define the number of solid, non-opened, segments at the start and end of the beam. Why is this important? There are two main reasons. Firstly, constructability, to ensure that the connection plates are not located within voids, which could complicate on-site welding or bolting. Secondly, structural performance. In some cases, especially when using moment-resisting connections, it is advisable to increase the number of solid web sections at the start and end of the beam. This helps prevent capacity deficiencies that could arise due to the shape of the moment diagram. Even though moment-resisting connections are less common for castellated beams, if you are connecting them to columns or other primary beams using rigid joints, this adjustment becomes important depending on the structural demands. Next, let's move on to the Load tab. Under the Wall section, you'll notice a small downward arrow icon. Clicking on it reveals predefined loads for different wall materials. You can see various load types available here. When you choose user-defined, you'll notice that the load unit is displayed as kilonewtons per square meter. You might wonder how the software calculates the total load. It uses the wall height parameter shown here, which, by default, is set to 2.5 meters. However, if you activate the auto wall height option, the software automatically determines the wall height based on the maximum section depth of the beams and calculates the clear span accordingly. Besides that, additional load definition options are available in the drop-down menu. Now, let's move on to the Curvature tab. This section works the same way as it does for steel columns. By entering a specific horizontal or vertical radius, we can model curved beams. We'll be doing that shortly, and I'll go over the details again when we get there. The next tab is Shear Studs. Since we haven't modeled any slabs yet, I'll explain this tab as a preliminary note. Why am I referring to slabs here? Because we use the Composite slab command to perform composite beam design. Once the slab is modeled, the number of studs placed along the top flanges of steel beams is taken into account during the design process. Currently, there is no slab modeled over the beam. In cases where a slab exists, the automatic stud placement option must be active for the software to detect and place the studs automatically. If you select the No Studs option, the software will perform the composite beam design assuming there are no studs, even if a slab is present. That's why it's important to check the settings in the Shear Studs tab for each steel beam. Now, let's go back to the General tab. I typed IPE 400 on the keyboard and pressed Enter. The section was reloaded. I clicked OK. You can model steel elements from either the plan view or the perspective view. In fact, when both views are open on the screen, you can mix both views during modeling. When I hovered over the steel columns, the cursor highlighted in a different color, a sign that you are snapping to a valid node. At this point, I'm on the ground floor. So if I start modeling from the plan, the software will place the element according to the elevation of the ground floor. But since I want to place my first element for the roof, I switched to the upper floor and reactivated the steel beam command. As you can see, I can input the beam from the plan, but let's undo that and try it again from the perspective view. There, at the connection points of the columns, the snap cursor again turned a different color, making it easy to visually confirm the nodes. Now I'll select the beam, and this is a good time to show one of the available commands. After selecting the beam, I went to the Divide command in the toolbar and clicked once. A dialog box popped up asking how many segments to divide the beam into and what distances to use from the start and end points. Here's what it means. For example, if I say, divide into 5 parts after 100 centimeters, the software takes the first 100 centimeters as a base length and considers it as a fixed segment. Then, it divides the remaining length into 6 equal parts. The same logic applies if you define the distance from the end. If you leave the start and end distances as 0, the program automatically divides the beam into 6 equal parts. I entered 2, which means the beam should be split at the midpoint. And yes, in the plan view, we can clearly see the 16-meter beam has been divided at 8 meters. I know that because the grid spacing was 2 meters. Next, I hovered the mouse to the intersection of the 2 segments. The cursor changed color again, which confirms snapping. I clicked and dragged the node. Now I can move it freely, and a small window appears, allowing you to enter X, Y, and Z values in meters. Since I want to create a sloped roof, I entered 1.5 meters in the Z direction and 0 in the X and Y directions. I selected global to apply this in the global coordinate system. That's how I created the slope. I'd also like to show you an alternative method for splitting beams. There is a second option in the divide command. Select element as divide point. To demonstrate this, I'll add an intermediate grid line and a new column. I placed the grid line 6 meters away from the starting point and then selected the steel column command. I kept the height at 9 meters for now and placed the new column. After that, I selected the newly created element and clicked the array command. The program remembered my last array settings. So I quickly completed the modeling this way. I selected the relevant beam and clicked the divide command. Below, it says, select element as divide point. I selected the column, and as you can see, the split occurred exactly at that reference point. By the way, I'm currently on the ground floor. But your current story doesn't matter for this operation. When modeling in the perspective view, you can interact with all levels. Now I want to model a separate beam next to it. I followed the same logic. In the perspective view, I clicked the two endpoints of the column. To better see the beam, let's enlarge the perspective window. Now, I want to model this beam as a cantilever. That means I need to enter an offset from the exterior face of the column. To create this cantilever extension, I need to define a custom working plane. I went to the View tab in the upper toolbar and clicked the arrow under Target Plan. Here, we can define 3 types of working planes: horizontal, vertical, or by 3 points. I chose 3-point selection, clicked the 2 ends of the beam, and then clicked the top node of the steel column on the next grid axis. This defined a new working workplane. Now I selected the beam again. I want to extend this end, and the coordinate box on the beam indicates the X direction. I grabbed the relevant node, entered 0 for Z, and 1.5 meters for X. At this point, you'll see 2 options: Finish Global and Finish in Active Work Plane. If you choose Global, the transformation is applied in the global coordinate system. But since I created a custom working plane, I want the transformation to happen within that plane, so I chose Finish in Active Work Plane. To exit this work plane, just right-click on an empty space in the window. You can now see a list of all custom and default working planes in the Workspace View Manager. I switched back to the perspective view. I selected the beam again and opened its properties. Just like in the steel column properties, you'll notice 2 new subtabs appeared. Since I want to create a curved beam, I navigated to the Curvature tab. I'd like to apply a vertical curvature to a beam with a 6-meter span. So I entered a 1,200 centimeters radius to achieve the slope. The beam was successfully modeled with the desired curvature. Now, whether from the plan view using a selection window, or by individually selecting them in the perspective view, you can select multiple elements. Next, I activated the array command. The software remembered my last used array parameters. I clicked OK, and the beam group was modeled successfully. Now, before continuing with the roof elements, I want to insert the framing objects on the intermediate floors. So I returned to the ground floor, went to the Steel tab, and activated the Steel Beam command again. This time, I selected IPE 270 from the toolbar. I'll demonstrate the modeling from the plan view. Let's zoom in a little. When you approach the nodes of the columns, the mouse cursor changes, indicating a snap. This helps make modeling easier and more accurate. I completed modeling all beams on this level. Since these members share the same section and span, I'll use smart modeling tools to speed things up. I selected one of the beams, right-clicked on it, and from the context menu, clicked Select. In the next window, you'll see different filtering options. You can select by layer, material, or section. For example, I chose to select all beams with section type IPE 270, since there are no other elements defined in the project that use this section. This became our distinguishing attribute. I clicked OK, and as you can see, both in plan and perspective, all matching elements are highlighted in a different color, indicating they've been selected. That's one option. Alternatively, you can use the Select Similars command. I clicked Custom Selection and used different filters, for instance, Load and Material. There are also options to filter by same X, Y, or Z location. In this case, if you look closely in the perspective view, these elements share the same Y-axis coordinate, so I use same location, Y-axis to select them all. Then I activated the Clone command from the vertical toolbar on the left. The command line asked me to specify a base point. I clicked on the first node, dragged to the second column node, and repeated the process for the next one. The operation completed successfully. Let's also finish the other row. This time, I'll use the Array command to quickly fill the span. The beam group is now fully modeled. Now, I'd like to create a grid system under the slab. If you remember, the spacing in one axis was 5 meters. I want to insert a main beam through the center of each span. To do this, I went to the Drawing tab and activated the Midpoint Snap command. There are also other options like Perpendicular Snap and Advanced Snap, but I chose Midpoint. I zoomed in a little and snapped to the middle of the beam. How do we verify it's the midpoint? I activated the Distance command in the Drawing tab, and we can see the value is 250 centimeters, confirming the midpoint of a 5-meter span. I selected that beam and activated the Array command again. The duplication process is now complete. Thanks for watching. Don't forget to like, subscribe, and explore the knowledge base for more tips. See you in the following video.